Everyone. We're continuing with reactions of alkenes and alkynes. I've suggested in class that you start perhaps keeping extra notes, maybe making a list to help you study, a study guide if you will, of all the reactions we have done so far, because today or in this lesson we're going to add several more. Okay. So a bit of review that we'll do in class before we get started with the lesson. During this video, however, we're going to skip over this, but in class we will do this together or online. Okay, unsaturated hydrocarbons. So those are the alkenes and alkynes I'm referring to in this lesson. Those ones are a bit more reactive than their saturated partners are because of those double and triple bonds. We'll later learn what pi bonds means, but that affects its reactivity. So a lot of the more common reactions that these will undergo are called addition reactions. These addition reactions occur because you have space for that. Again, more detail in our second unit, but more space for those other bonds to be added, for other atoms to be added onto that unsaturated double or triple bond. Okay, now this is a picture that will certainly mean a lot to you in our next unit, so I'm going to skip over this just for now and head to our first reaction. So a halogenation reaction, or an addition reaction with a halogen, looks something like this. This is a common example. We have an alkene here, ethene, commonly known as ethylene, in the presence of a halogen, bromine, for example, bromine gas, remembering your Hofbräunickel from grade 9 and 10. Also in the presence of a catalyst, carbon tetrachloride will saturate this alkane, giving you an alkyl halide, 1,2-dibromoethane in this case. Okay, so what is needed for a halogenation reaction? This is the general form, so this can be any alkene where R and R prime are just ends to this carbon that could either be the same or can be different. So this is a general form of an alkene in the presence of a halogen. Okay, and our catalyst is carbon tetrachloride. That will saturate that double bond, creating an alkyl halide where you have those two halogens attached to either side of what was that double bond. Okay, again, carbon tetrachloride is your catalyst. So another example, here we have an alkyne following an addition with a halogen or halogenation. Again, we have bromine here, our halogen, carbon tetrachloride, and what happens is we go from an alkyne to an alkene, but it now has bromine added onto it. So it's slightly more, it's been saturated at this one step from an alkyne to an alkene. I shouldn't say saturated. It's this addition reaction has created an alkene from an alkyne. Okay, if it reacts once more in a similar condition with carbon tetrachloride, a halogen, then it becomes fully saturated, right? And we see another pair of bromines added onto that to either side of this double bond, and we get a saturated alkyl halide, right? So this reaction can continue in one step with alkenes and in two with alkynes. Okay, so that is our first reaction. Our second is hydrogenation. So hydrogenation, without going too much into this, it's why you have certain synthetically made fats, such as margarine. Now, even though margarine companies might want to convince you that they are healthy and that they are made out of olive oil, let's say, or have omega-3s in them, that's all sounds really good. But the process, the chemical process, and although it has gotten better from what I know in recent years, or maybe even more than that, it is still artificially made, and it is not processed by your body, by your cells, as compared to something that is actually natural. So take that information and do with it what you will, but this is what hydrogenation looks like. So an unsaturated hydrocarbon, say an unsaturated oil at room temperature, can be turned into something like margarine, solid at room temperature, if you hydrogenate it. So hydrogenation takes place when you have an unsaturated hydrocarbon like this ethene reacted with hydrogen gas. You bubble some hydrogen gas through a large vat with a catalyst, nickel, palladium, or platinum. And that allows for this unsaturated hydrocarbon to become saturated. Now, the problem with this, and we'll get more into it when we look at isomers, is that this can create geometric anomalies called kinks or trans, when referring to oils, trans fats, which your body does not do well with at all. So be careful when you're deciding or even consuming or deciding to consume any artificially made fats, hydrogenated fats. Okay, so an example. Here we have an alkene, 1, 2, 3 propene, right? 3 carbons long, alkene right here, or double bond here, in the presence of hydrogen gas and a metal catalyst. Again, our options are nickel, palladium, or platinum. We then get a saturated or saturation of this alkene into an alkane, generally. And like halogenation or addition of a halogen, this can happen in 2 steps. If we begin with an alkene, right, that catalyst is referring to your metal catalysts, you will want to write a specific metal catalyst. So if you're asked to write a reaction, don't just write catalyst, you'll need to pick one. Nickel, palladium, or platinum, whatever you desire. Okay, so this alkyne will turn into an alkene, and it can undergo another hydrogenation reaction and become an alkane. Okay, again, don't write catalyst, choose one. Now, how it does this, without getting into too much detail in this video, we will in class. The metal catalyst offers a surface that can stabilize this reaction and its reaction intermediates, its chemical intermediates that lead to the final saturated product. So here we have a catalyst. Let's say it's platinum, the more expensive of them all. Platinum will then absorb some of the reactant material. So the hydrogen gas can stabilize these hydrogen bonds, right? Because of and we'll talk about when we get to types of solids later on in the course, why it can do that. Little hint, the electron C theory, electrons within the metal surface can stabilize these hydrogens. And in the presence then of an alkene, can also stabilize that pi bond or that double bond in the alkene, keeping it partially broken, partially formed, partially not, allowing for the hydrogen to react with it, right, to lower the energy required during this reaction. So one hydrogen gets attached, slowly saturating this alkene, while another one does the same to the other carbon, and we have a then fully saturated alkane, and the catalyst just served as the surface to where the stabilization of this reaction happened, right, and can therefore be reused. Next reaction, we have an addition reaction with a hydrogen halide or hydrohalogenation. Hydrohalogenation, look at an example, hydrogen and bromine, hydrohalogenation. Okay, so that gives you a clue of to what is being added onto an alkene. So we're going to saturate it with hydrohalogenation. I made reference to this in a previous lesson, I believe it was on alcohols. And how one of the examples was a competing reaction. Well, here it is. I said we would go over it, and we're going over it now, more formally though. So in the presence of a hydrogen halide, we will get hydrohalogenation. Notice there are no catalysts. There have been for other reactions, every other reaction we've looked at, not in this case, but it does follow Markovnikovs rule. So you need to two products will be formed. One is a major product and one is a minor product, and it's going to follow Markovnikovs rule where the carbon with the most number of hydrogens continues to get more hydrogens. So let's look at that. This carbon here, let's take out a highlighter. Okay, this carbon has 2 hydrogens, 1, 2. This carbon has 1 hydrogen. So the carbon with the most hydrogens will get another hydrogen. So let's go to our pen. The hydrogen, I do have that selected. Okay, the hydrogen will go here. I think I've moved it. We'll wait for that to settle down. Okay. I'll delete that. Sorry, little technical thing happening here. If I can find my cursor. Okay. Hydrogen will go to that carbon. while the bromine will go to that carbon. Just got to fix my pen here. Bromine will go to this carbon. And in that example, you then get your major product. Now, to get your minor product, it's just the opposite. The hydrogen will attach to the carbon with the least number. So that's your minor product. So your major product is here, 2-bromopropane instead. Okay, now if I can find my cursor, here it is. We can move on. Right, so generally this is what a hydrohalogenation will look like. Here you have an alkyne. And again, this is left, just we're trying to show you different examples of how you might see this. So instead of an R here or an R prime, these dashes just mean any general form of an alkyne. Now an alkyne with a hydrogen halide, now this is a keyword in excess, means that there's lots of it. So it will continue reacting until it is complete and can't react anymore. It will then go through, and I'm missing a step here, but it shows you it's going to go from a alkyne to an alkene, then to a fully saturated alkyl halide. Okay, maybe I'll show you actually the step that I'm missing here. So an alkyne, no catalyst present, one gets the hydrogen, and one gets the halogen. There you go. This will react once more with the same hydrogen halide to form our completely saturated alkyl halide. Okay, now this reaction we've actually seen before. This is an addition with water to create an alcohol. So when we did our alcohol lesson, we saw that an alkene in the presence of water and an acid, H+, or you can also say H3O+ as hydronium, or usually H2SO4 as the strong acid used as a catalyst in a reaction like this. Okay, and it continues, of course, to follow Markovnikovs Rule. Okay, so sulfuric acid is usually used. Now, for our purposes, you can write H+, that's perfect. You can write hydronium, or you can write sulfuric acid. Either one of those will work just fine, and you will get full marks. Okay, now reviewing Markovnikovs rule again, although we have talked about it before, look what happens. The carbon here has 2 hydrogens, and the carbon here has 1 hydrogen. Therefore, this first carbon over here to the right is going to gain that hydrogen. Look, it does. That means the other carbon will have the bromine, and that is then your major product. Now, if we flip these, it becomes our minor product. But according to Markovnikovs rule, the major product is this one. Okay, just another example for you to refer to. Basically, I know I've mentioned this in class, hydrogen will attach itself to where there is more of it. There's a saying that is probably unfortunately true, but the rich get richer. In this case, the carbon that has the most hydrogen will get more hydrogens. Okay, that's really it. Now to review, you should be able to summarize these for all the reactions we've done. What reactants are generally involved, in this case it's alkene or alkyne, so that's all set. What catalysts or conditions are necessary, and then what products are produced. So these are the reactions to review. So for hydrohalogenation, we found that we need a certain catalyst, right? Hydrohalogenation, it's okay to go back and see. For a hydration reaction, we reviewed last time. For halogenation, and then for hydrogenation, you should know reactants, catalysts, and products. Okay, so probably good. Pause the video now. Do I know these? Okay, next, that's it. So you can continue practicing, looking at referring to your worksheet on alkenes and alkynes posted online. Hope this helped. I'll see you in class.